Okay, so let us talk about the properties of maximal strongly connected components. Okay, so first property of maximal strongly connected component. If S1 and S2 are two different MSCCs of a graph, then S1 intersection S2 better be the empty set, which means that maximal strongly connected components cannot share a vertex. If they are different maximal strongly connected components, they cannot share a vertex. Why is that? Let us take an example. So suppose you had a vertex in common between the two MSCCs. So let us have MSCC 1. Okay, so bunch of vertices, MSCC 1. All right, and what's the idea here? It's full of these cycles. You can go from one place to another. And let's have MSCC 2. And this node that I've shown here, let's say, is in common between the two MSCCs. All right. Now the problem here is that suppose I had two different MSCCs. Okay, two different MSCCs. So they are not both the same MSCCs. So they are different. At least something is different. But let us say that they have some vertex in common, at least one vertex in common. Let's call this vertex V. Well, the problem is, if I take any V2 here in the second MSCC, well, there is a path from V to V2 and V2 to V. That is why it's a MSCC. There are paths here. And likewise, if I took a vertex V1 here, well, there is a path from V1 to V and V to V1. And therefore, let me take S1 union S2. Take S1 union S2. If I took any two vertices in S1 union S2, then there exists a path from V1 to V2 and vice versa. And this path only involves nodes in S1 union S2. How is that? Well, from any vertex V1, first get to V. From V get to V2. So that's how I can hop from V1 to V2. If I wanted to hop from V2 to V1, hop from V2 to V and from V to V1. So I can hop. Therefore, S1 union S2 is a larger SCC containing S1 and S2. So here is a bigger SCC that subsumes S1 and subsumes S2. So which means that the M part of the MSCC can be attacked. So therefore, S1 cannot be maximal or S2 cannot be maximal. And that yields a contradiction. So because that yields a contradiction, you cannot have things in common between S1 and S2. So if you have two different maximal strongly connected components of your graph, they cannot have a vertex in common. They must be disjoint. Let's take a look at our graph here as our example, 2, 3, 4, 5, 6, 7, 8, 9. So they are disjoint, right? So they are disjoint maximal strongly connected components. Okay. So therefore, if you take a graph and you start writing out its maximal strongly connected components, each vertex can only appear in one of them. If you take the vertex 4, well, it only belongs to one of the maximal strongly connected components. If you take the vertex 6, it only belongs to one of them. And by the way, every vertex must belong to some maximal strongly connected component. And if not, we allow for it to be a trivial MSCC by itself, right? So 1 here belongs to a maximal strongly connected component of itself. So because we allow that, the set of maximal strongly connected components partitions the vertex of the graph. So S0 union S1 union S3, in this case, I should have named it S2, I named it S3, is the set of vertices of the graph. So if you take the union of all the maximal strongly connected components, that forms your entire vertex set of your graph. And if you take the intersection of any two, that's the empty set. So together they partition the graph into many disjoint subsets, and these subsets are called the maximal strongly connected components. Now we get to a very interesting bit of terminology. What is that interesting bit of terminology? Well, the interesting bit of terminology is the word maximal in front of the SCC. So in many books, when they say SCC, they actually mean MSCC, okay, and that is kind of confusing. Some books will say strongly connected components and they mean maximal strongly connected components. I am trying to be a little bit pedantic here to decompose the two aspects of the definition. One aspect is the notion of a strongly connected component, and the other aspect is the notion of a maximal strongly connected component. Okay, so we will simply say maximal throughout my lectures, but note that in many books, in many presentations, just a strongly connected component, already they mean a maximal strongly connected component. So it's a notational thing that people sometimes cannot agree upon. So I will keep saying maximal just to remind you of what I mean. But note that many people will say strongly connected component, in which case you might want to ask them whether they mean maximal strongly connected component, and typically they will know what you mean. All right, so this is how it goes. So this is the first property of MSCC, that they are pairwise disjoint. What's the second property of MSCC? Well, it's closely related, and this is also a very important property. Okay, so let me make space for this property. So this property says, okay, you can, making some space, almost there. All right, there we go. Okay. All right, what's the second property? Well, suppose in this graph, I take each of these maximal strongly connected components and I build what is sometimes called a supergraph, or people will call it an MSCC supergraph, which is take every maximal strongly connected component and compress it into a single node. So 1 becomes a node by itself, 2, 3, 4, 5 becomes a node by itself, and 6, 7, 8, 9 becomes a node by itself. All right, and then let me add the connections that only go across MSCC. So there used to be an edge from 1 to 2, and now that's an edge from 1 to the entire 2, 3, 4, 5. There used to be an edge from 2 to 6, now that becomes an edge from 2, 3, 4, 5 to 6, 7, 8, 9. Are there any other edges we should worry about? No, there's no other edges. Every other edge is internal to MSCC, so we leave them out. Okay, and this is called, sometimes called, not everyone wants to call this is called an MSCC supergraph. All right, just decomposing every MSCC, compressing it into a single node, you get a new graph which looks like this in this case. Well, this is the second important property of MSCCs, which is the MSCC supergraph, okay, is a directed acyclic graph. The main important thing is it is acyclic, cannot have cycles. And that's super important to note, that this MSCC cannot have cycles. Why cannot it have cycles? Well, let us imagine that your MSCC supergraph had a cycle. Okay, so there was a cycle. So what does it mean? It means that in some graph you could go from, let me say, some MSCC M1. Let's say I could go from there to M2, all the way to some MK, M sub k, back to M. Okay, so suppose there was a cycle in this graph, in this supergraph. Well, unfortunately, now consider M1, consider the union of all the nodes along the cycle, M1 union Mk. Well, if I start from any vertex in M1, well, there is a path to the head of this edge. Wherever this edge went, there is a path to the head of this edge. From there I take the blue edge, and then inside M2 there's going to be a path to the head of the next edge. And if I keep traversing, what you notice is that this whole union is an MSCC. Why is that? Because if I wanted to go from any node to any other node, like some node in M1 to some other node in MK, well, there is a way for me to get there. I hop from one MSCC to the exit. From the exit I hop to the next one. I hop to the exit, I get to MK, the entrance of MK, and from there I will find a path, because each of these M1, M2 to MK are themselves MSCCs, right? So I can go from anywhere to anywhere else. Likewise, I can go from any node in MK to any node in M1 to any node in M2. So because of that, this entire union becomes an MSCC, which is larger than each of them individually. So it's larger than M1, strictly larger than M2, strictly larger than MK. These are not empty sets, right? If not, then it contradicts the fact that each of them is maximal. Maximal means they cannot be extended anymore. But if there is a cycle in this graph, well, the entire cycle will collapse to a single big MSCC, which is the union of all these small nodes, and that cannot simply be. And so therefore, it is an acyclic graph. So there cannot be a cycle in this graph. It's an acyclic graph. Okay. So interestingly, a lot of algorithms have this combination of taking the maximal strongly connected components, constructing some kind of supergraph, and then doing some kind of topological ordering on the supergraph. So that is, for example, a very standard approach in many algorithms, okay, that comes up all over the place, for example. And you can do that because it's a DAG. The supergraph is a DAG. It's a directed acyclic graph. All right, so two very, very important properties of maximal strongly connected component. Now finally, there is a third property, okay, and I'm simply going to state this property, and I hope you have learned enough now that you should be able to do a proof of this property, okay. The third property, which is all important, is that the reverse graph G transpose has the same MSCC as the original. Let me explain what is the reverse graph and why do we put a transpose on it. Well, in the reverse graph, you take the original graph and reverse the direction of every edge. Okay, I'm showing it in green. You simply reverse the direction of the original edge. So they are all now in green. So that's the reverse graph. Okay, take the original edge and just reverse the direction. Okay, how do we do that with an adjacency list? In the adjacency list representation, you have to iterate through each edge in the adjacency list and create a new adjacency list where you add the reverse edge. Okay, I hope you know how to do this in the adjacency list. How do you do it in the adjacency matrix? Well, if you have an adjacency matrix of zeros and ones, you simply transpose the matrix. So you turn all the rows into columns and columns into rows, and that becomes the reverse graph. And that's why the notation for the reverse graph is G transpose. You transpose the adjacency matrix, you obtain the reverse graph. Okay. And for adjacency list, it's a little bit more time consuming than transposing, but you know how to do it. I hope you know how to do it. All right. Now the claim is, if I reverse the direction of all the edges in the graph, I still get the same set of MSCCs for this new reversed graph. Why is that the case? Well, first, it's easy to see that every MSCC will remain an MSCC. Why is that? If I could go from 2 to 4 in the original graph, I could go from 4 to 2 in the same way in the reverse graph. If I go from 2, 3, 4, I can go 4, 3, 2. Right? So, and likewise, if I can go from 4 to 2 in the original graph, I can go from 2 to 4. So the definition, from the definition of MSCC, you notice that reversing the direction of the edges keeps an MSCC and MSCC. So the MSCC property is preserved under reversal of edges. And furthermore, you also notice that if it was not an MSCC in the original graph, so for example 1, 2, 3, 4, 5 in the original graph was not an MSCC, in the reverse graph it will still not be an MSCC. So MSCCs remain MSCCs, not MSCCs remain not MSCCs, and therefore you can combine these two arguments to prove that the set of maximal strongly connected components are not altered when the direction of the edges are reversed. And that's super important, and that's the third property. All right, now that we have these three properties, we can now do depth first search to discover all the maximal strongly connected components of a graph. And given a graph G, the goal is to print 1, and then print 2, 3, 4, 5, and then print 6, 7, 8, 9. So I want to print the set of strongly connected components of a maximal strongly connected components of a graph given the graph in, let's say, the adjacency list representation or adjacency matrix. Doesn't matter, I want to print out all the strongly connected components, the maximal strongly connected components, not just the strongly connected components, okay? We are making the distinction for the purposes of this lecture, even though the book does not make that distinction. I hope this is all clear. If this is all clear, we can move into the algorithm in the very next lecture. See you then. Bye.